All right, so today we're going to take a look at 3.8, which is a section in your textbook called implicit differentiation. And the reason why we're starting with this and not 3.7 is because I think that 3.8 ties in very closely to the chain rule that we just learned last week, okay? Now, I think folks did overall a pretty good job identifying that chain rule on quiz number 6. But I just want to make sure that it's something that we are actively looking for and something that we sort of know, okay, not just when should we look for it, but how do we execute it? Okay, and so I think this lesson will actually tie in really well to that to get us thinking about why chain rule is so very fundamental. So let's get started with what we know. How is the sound, by the way? Is it lagging? Are we okay? Seems good. Okay. I was having some trouble the other day with the internet, so I just want to make sure it's okay. All right. So what do we know? Kind of a checklist for that upcoming exam this week, but also thinking about how much we've actually accomplished over the course of the summer so far. So we've talked about average versus instantaneous rate of change, that formal definition of a derivative. And more recently, we focused a lot on all these rules, so many rules. Power rule, constant rule, product rule, quotient rule, all these different kinds of rules, okay? And in particular, the one that I really want us to think about is our chain rule that we took a look at on Thursday of last week. And so one thing that we learned about chain rule was when we were taking a derivative of a function that had another function inside, right? So f of g of x, we had to take the derivative of the outside, right? So f prime. But what did we do with the inside of that function? Like to finish off writing this, how did we handle that? Right, so we were super patient, right? As Matt said, we left the g of x inside. And so f prime of g of x was the first part of it, right? This was our derivative of the outside function. And then how did we compensate for the fact that we had a g of x on the inside? Good. All right, so I see a couple variations here. We are correct that we then had to take the derivative of the inside piece, and we just want to make sure that we are multiplying by the derivative of the inside, okay? And in particular, when we're thinking about quiz number 6, there was a question, and gosh, I forget which one it was right now. Let's see, can I pull this up? There was one question where I had you working from the table. So this is like number 9 from quiz 6. Asked you in symbols, basically, how could you find that or express the derivative of a function that had another function inside of it, okay? Now, folks did overall very well on that question. We just wanted to help us make those connections between what we're learning in terms of like all the rules and where it might correspond to on an exam, okay? Now, what is new today? We are considering situations where we have equations that are not y equal, okay? And so in particular, what we're looking at is cases, so situations where, whoops, y is mixed into the equation, okay? So we'll take a look at a lot of examples, but basically we'll have something where x's and y's are all mixed up together. And sort of a secondary point, it is challenging to isolate y, okay? So if you're thinking and you're preparing for the exam and you're like, how am I gonna know that I'm supposed to use implicit differentiation? Okay, so implicit differentiation, that's our topic for today. 2 clues for you is you're gonna look at an equation, x's and y's are gonna be all mixed up together, and it's gonna be really hard to get y by itself, okay? So if you see those 2 things, you should be thinking, that's gonna be section 3.8, implicit differentiation, okay? All right, so to start off, we're gonna take a look at some patterns, okay? I'm really big on patterns because I think you folks know so much more than you think you do sometimes. And if we look at patterns, sometimes we realize how much more we actually do know, okay? And so let's start off with this example number 1, right? So we're gonna take a look at 5x cubed minus 7x plus 1 to the 5th power. And I'd like you to tell me what rule or rules you think we should use to find that derivative. Right, so I already see a chain rule. Chain rule, yeah. What other rules might we need?
Power rule.
Power rule, I agree, because I see like something to the 3rd power. I see an x to the 1st power. Yeah, constant multiple would be good. I see a sum and difference. Okay. Now I see someone has said that maybe product rule. And I might imagine that someone might say for 5x cubed, we need product rule. But what might be a rule that is a little bit more efficient to use instead of product rule for that 5x cubed? Yeah, we could use that constant multiple rule, right? Because we have a 5, and then we could multiply that by the derivative of x cubed, all right? So some places we might see product rule, but we always want to choose the one that's going to be the most efficient, okay? All right, so let's find this derivative, all right? If you were to tell me what the derivative of this expression is, I'll give you a moment. You could try and type that into the chat and let's see what we get. Okay, this will be a really good review of what we learned on Thursday last week. I see part of the derivative. Okay, I see part of it. 15x squared minus 7 should be somewhere in our derivative. And what would we, let's actually tie that back to what we wrote for this chain rule above. Is that the f prime of g of x or the g prime of x? Yeah, that would be the g prime of x. Good, good, good. Okay, so if we follow what we wrote above, we can say that we're going to take the derivative of the outside. So we're going to do that 5 power first, okay? And then at the end, we're going to multiply by the derivative of the inside. So that will give us, let's see if I can manage to write this here. 5 5x cubed minus 7x plus 1. Good. I love that we all remembered to the 4th power. That's so, so important. Times the derivative of the inside piece, which is what Sophia gave us, which is that 15x squared minus 7. Okay. And I cannot for the life of me remember what colors we used on Thursday. So we're just going to pick new colors. This would be our f prime of g of x. And then this would be our g prime of x. Okay. All right, so really great job remembering that we need and recognizing when we can use chain rule, okay? And listing all these other rules. Part of that's for vocabulary, and part of that is just so we really connect the ideas of what rules we're using and when we use them, okay? So let's move down to this second expression. I have g of x to the 5th power. And I'm wondering if you can tell me what rule or rules we need to take that derivative. All right, Alberto says we're going to need that chain rule. I agree.
It's all the same rules, right?
I think we need chain rule.
Oh,
What other rules might
yeah.
we need? All right, good. I think we need power rule as well. I love it. Okay. Now, one thing to notice here, though, I don't know if I need a constant multiple rule because we don't actually know by what g of x is, right? We don't know if we need sum or difference because nobody told us what g of x is. And similarly, we don't know if we need the constant rule because we don't know what g of x is, okay? And so there's fewer rules here, but we can still find our derivative, right? How would you express this derivative, g of x to the 5th power? All right, nice. In fact, it feels very similar to what we just wrote, right? Shoot. Hang on 1 second. Okay, hold on. All right. Okay. All right, so it looks really similar, everything that people are saying, to what we had written down for the first one, except that we have 5 g of x to the 4th times g prime of x, okay? So super similar structure going on here. And we have one last expression, this y to the 5th. What are our thoughts? How might we write the derivative for y to the 5th? Ooh. I could not have asked for 2 better answers to be thrown out into the chat. Okay, so power rule. I would agree that we're gonna need power rule because we have y to the 5th, okay? Now, what if I told you though, that y is not just a variable, but y represents a function, all right? So where y represents a function. All right, so if y represents a function, okay. So Sophia, how would you like to modify your answer? Because you typed in 5y to the 4th. Yeah, I think so as well. 5y to the 4th is really similar to g of x, like 5g of x to the 4th. But then, just like we had to compensate for g prime of x, that derivative of the inside, we also need to compensate for the derivative of y, okay? So here, we're gonna say power and chain because our y represents a function, okay? So let me just pause here for a moment. How are we feeling about this progression? We had one that looked very similar to what we had on Thursday. Then we made it a little bit more abstract, and we kind of saw some of that on like quiz 6. And then we replaced g of x with a y. And it turns out that all 3 of our derivatives follow the same pattern, 5 something to the 4th times the derivative of that something, but we just were able to fill in less and less when we had less and less information. So if you want to give me maybe like a quick thumbs up or thumbs down in the video, so on your screen, I can kind of see how we're feeling. Great follow-up questions. I love it. I love it. Okay, so whenever it's a function, we should imagine parentheses around it. Exactly, exactly. So maybe this would have been more clear if I had written this as y to the 5th. Like there's some function there. Okay, and I see a follow-up question. Every time we see y, we treat it as a function. Yes, every time we see y, we're going to treat it as a function, okay? And implicit requires the chain rule is such a great summary. In fact, let's maybe go back up here and make a note for ourselves that this requires chain rule, okay? Now, I don't want us to think about that in a bad way, like, oh no, we have to use chain rule. I would love for us to think more like, wow, this is another chance for us to practice that chain rule, the super important rule that comes up all the time. And not only does it allow us to solve chain rule problems, but now there's a whole nother class of functions that we can also find the derivative of, okay? All right. We get to use the chain rule. Exactly. It's so special. We totally get to use the chain rule. All right, so implicit differentiation is just finding the derivative. We don't have to solve the derivative any further. I'm not really sure what you mean by solve the derivative. Can you clarify that for me? Maybe while we're thinking about the clarification, let's go ahead and try what we just did in example 1 with a different expression. Oh, okay. So it depends. We're going to see this in the context of bigger problems. So when we actually do a problem, let's maybe come back and ask ourselves those rules. Does that make sense? Okay, so right now we're just setting up the concept, like how do we apply what we already know in a new context, but then we'll go through some practice problems where we actually see questions that'll be similar to the quiz, okay? All right, so sine of 3 minus 6x. What rule or rules do we need to find that derivative? Yep, I agree. We're going to need trig. What else? Oh, chain rule. Anything else? I'm going to throw constant and constant multiple in here. But I think we're reaching a point where we don't need to write constant and constant multiple as much, okay? My hope is that those have become more second nature to us, that it's a little bit easier for us to see when we're going to need constant and constant multiple. Whereas something like trig and chain is a little bit newer for us, and I want us to really work on recognizing that, okay? And so what is that derivative? What is the derivative of sine of 3 minus 6x?
It's a 6 cosine 3 minus 6x.
Super close. We've got a 3 minus 6x here, so that derivative of that is going to be negative 6. Yeah, okay. So exactly. We're going to have our cosine of 3 minus 6x times negative 6. And maybe the only thing we would simplify there is just bring that negative 6 to the front, okay? Excellent. All right. What about sine of g of x? Which rules do we want to keep from that first part? Yeah, I would agree. The first two, the trig and the chain. And what is that derivative? Cosine g of x times g prime of x. Nice. Cosine of keep the inner function times the derivative of that inner function. Great. All right, last but not least, sine of y. What rules do we need and what does that derivative look like? I think same too. We're gonna need trig because of the sine. We're gonna need chain rule because we sort of have this inner function, right? Remember, y represents some function. So how would we represent that derivative? Good, we're gonna have cosine of y times y prime, okay? And so think back to in your academic career when you only knew about x's and y's and the very first time your teacher was like f of x or g of x, right? We're almost kind of going backwards where we're like, sometimes we're just gonna write y instead of g of x or f of x, okay? All right, let's do one more set just to make sure we really know our rules. So let's do rules for this first one. E to the x squared minus 9x. Not a fan of these ones, okay? We are gonna need chain rule. We are gonna need chain rule. And the reason why we need chain rule is it's not just e to the x, but it's e to some power. And I agree, we're going to need the power rule for that x squared. And then we could think constant multiple for that minus 9x. Okay. What makes these ones like feel weirder for folks, saying like, oh, I don't really like these as much? I'm just curious. Well, there is that video. You are always welcome to ask me questions about the video, okay? But sometimes we do need to, you know what though? I feel like they're so underrated though. E's have so many special rules that make things a lot easier. But I think maybe sometimes it's weird because it's like a number, but it doesn't look like one. All right, what do we think about this derivative then, given those rules? I think we've got e to the x squared minus 9x, like we still have that part. That might be what we consider the derivative of our outside function. Good. And then time, what's the derivative of our inside function? Good, 2x minus 9. Okay. And that would be absolutely fine to leave it like that, okay? All right. Let's take a look at e to the g of x. I think we can keep that chain rule. Ooh, we didn't write down exponential and our exponential. But how would we represent the derivative of e to the g of x? Good, right? It's so similar to what we have up here, except instead of x squared minus 9x, I just said there's some function up there. I don't know what it is, but there is one there. And so when I take that derivative, I'm going to need to compensate for that by using the chain rule, okay? Now, last but not least, what am I going to do for e to the y? Good, chain and exponential. All right, and how would we write the derivative of e to the y? Good, e to the y times y prime, okay? Good. All right, so what's the takeaway? We kind of wrote this earlier, but since y is a function, okay, so since y is a function, we should use chain rule anytime we have, we are finding the derivative of an expression with y, okay? So since y is the function, we should use chain rule anytime we are finding the derivative of an expression with y, okay? And so with that, let's go ahead and try our very first example, okay? So we're gonna do this example and then we're gonna take a short break. all right? But what I like about this example, maybe you like this, maybe you don't, but like many of the other things we've done, there's more than one way to find the derivative. And so we're going to practice finding our derivative in two different ways, making sure that they match, they give us the same thing, and thinking about when we might want to use which one, okay? So would we like to see implicit differentiation first? Or would we like to get y by itself first? How are we feeling this morning? Okay, so we have, okay, all right. We have some mixed reviews, but mostly people are saying, let's get y by itself first. Okay, so method number one for us will be isolate y, then find the derivative. Okay, so we're gonna isolate y first, and then we're gonna find our derivative. So xy equals 1 is our function or our expression. If I'm going to get y by itself, I'm going to divide both sides by x. So y equals 1 over x. Yeah. Now, before we can use power rule, though, it would probably be valuable for us to rewrite this so that we can very clearly see the power as x y equals x to the negative 1. Okay. All right. Then we're going to take our derivative using the power rule. All right. Now I see a lot of people typing in what happens over on this side. And I see Matt coming in to write a y prime there. And some of us got our quizzes back. And maybe if you've read what I wrote down, I was like, you need to write y prime here. And you might have been like, why is she so picky about this stuff? Man, why does it matter if I write a y prime or not? She knows what I mean. This is the moment when it's going to be like very critically important that we write out that y prime, okay? We all know we use the power rule on this side. What is the derivative of y? Okay, so when I apply the rules, here's my equation. Whatever I do to one side, I have to do to the other side. If I'm going to take a derivative of the x to the minus 1, I'm also taking the derivative of y. And so when we take the derivative of y, we get y prime. When we take the derivative of x to the negative 1, we get negative x to the, I'm actually going to write this out because not a lot of you, but a few of you, and I'm not going to put you on the spot right now, a few of you have been adding incorrectly here in your powers, and you've been getting some strange answers, all right? So if that was you, just, this is for you. Please write that out so that you don't make that mistake. But you should end up with y prime equals negative x to the negative 2, or as Sophia has simplified, y prime equals negative 1 over x squared. Okay, this, my friends, is the full answer. If you're not writing this side, you don't have a full answer. And up until this point, it hasn't mattered that much, but it's about to start mattering. Okay, so part of this pickiness on my end is like, I want to set us up for some really good habits. All right. So how are we feeling with this method? We solve for y, we take our derivative, we're going to be really clear about our notation so that whatever we do on one side, we're doing on the other, and then we're rewriting our negative exponents. I see a couple thumbs up. Why wasn't chain rule used in this example? That's a great question, Joey. If I look at this y equals x to the negative 1, that looks like a question that we solved maybe last week, like when we first started learning about derivatives. I don't see an inner function and an outer function. Like it's not like sine x to the -1. Yeah, or it's not like x to the 10th to the -1. Yeah, exactly. And I really like that you said that, Abby, that we could use the quotient rule, right? If we think about this, you 100% could use the quotient rule, but what's going to be faster? Turns out if we use a little bit of algebra to rewrite, then we can use the power rule. It might end up being more efficient, okay? But the questions that you're asking are so great because that's what I've been trying to create with these discussions, right? I want us to start to think, I could solve it this way, but I could also solve it this way. And sometimes when we're like using internet resources, they don't always use the most efficient way to solve something. I want us to be a little bit smarter about that, right? I want us to say, yes, I could do it this way, but that resource is not as fast. I could do this way and it would be faster. Okay. All right. So now that we know what the answer should be, let's think about the second method, which if we do it correctly, we should end up with the same exact answer. All right, so we're going to take a look at method number 2, which is implicit differentiation. All right, and so what we're going to do is we're not going to isolate anything. All right. Actually, that's a really good point. So someone just asked, isn't chain rule used for the derivative of y? I would say technically yes. The derivative of y is just going to be y prime. Okay, so it'd be 1 y prime. All right, so if I just gave you this function, xy equals 1, I would read this left-hand side as x times y equals 1. And as soon as I say x times y, what rule would you think I'm trying to get you to use? Yeah, I'm secretly saying, over here, I'm gonna want you to do the product rule, okay? If you're doing the product rule or the quotient rule, I do want to see that setup part, okay? So I do want to see if you call it U and V or F and G, either way is fine, but let's just make sure that we are showing that step, okay? So U and V, and we're gonna need a DU, and we're gonna need a DV, okay? So what is our U in this case? U would be X. And what does that make our DU? Good, good, good. Okay. What about our V? Good, that's going to be Y. And what about our DV? Yay! I've never been so happy to see so many Y primes there, okay? So when U is X, DU is 1. But when we have V equals Y, DV is going to be Y prime, okay? All right, let's plug all of this into the product rule. We're going to get U dV plus V du, or whatever iteration of it. Now that is a good question. I've been waiting for that question. Why is the X also not X prime? Anyone have any ideas around that? Yeah, it really boils down to all these rules that we made up. Well, we didn't make them up, but all the rules that we've been using, it depends what we're taking a derivative with respect to, okay? And so we are taking derivatives with respect to x, meaning x is the variable. And so whatever the variable is, that means all the rules are fitted for that variable. But y is really, what is y? Y is actually 1 over x. I just didn't write it that way. And so if I want to find the derivative of y, well, that's a function. So then I have the y prime. But all of these derivatives that we're doing are with respect to x. So x is the variable, not the function. Does that make a little bit more sense? That is a super valid question, by the way. Okay, thank you. All right, so on the left-hand side, right, x, y, I'm going to use the product rule. But because I've been like, let's be so picky about that notation, exactly, Matt, we have to set it equal to the derivative of the right-hand side as well, okay? And so the derivative of 1, and see if we write it like this, derivative of 1, that's going to give us 0, okay? All right, so let's plug in everything that we have. X, y prime plus y times 1 equals 0. So far, so good. We set up our product rule. We took for the left-hand side. The derivative of the right-hand side was a little bit easier because it was just the constant. And then we just substituted everything in this last line that we wrote. All right. So here's the deal, folks. Our calculus is done. Like we've taken our derivative, okay? But I told you earlier the answer was negative 1 over x squared. So how come we didn't get the same answer? Well, turns out that in order to show the same answer, we need to do a little bit of substitution and we need to isolate our y prime, okay? So I'm going to go ahead and get y prime by itself over here. If I'm going to get y prime by itself, I'm going to subtract this y and move it to the other side. I'm going to get x y prime equals negative y. And then how do I get that y prime by itself? I got to divide both sides by x. So y prime equals negative y over x. Well, that still doesn't look the same as what we had before. We have one last thing that we can do to make them the same. And that is, remember when we said y equals 1 over x? Yeah, everywhere we see the y, we're going to put 1 over x. So y prime equals negative 1 over x. And when we clean that up, we get negative 1 over x squared, which matches what we got using the other method, okay? Okay, so now this question was picked because we could use both methods, right? And I wanted us to sort of have an idea of where we wanted to go, practice a simple case of the new method, and then be able to show that the two answers were the same, right? But Abby asks a very important question, which is, are we always going to be able to replace the y? Like, can we always solve for y? Because if we can solve for y, we might as well have just solved for y and then taken the derivative, right? Turns out that we're not always able to do that. And we're going to see very quickly, as soon as we come back from break, that this method is not always possible. And in fact, if we go back up to the top, where we sort of had two clues for when we're going to use implicit, x's and y's are sort of mixed up together, but this second part is really why we need to use this implicit differentiation. It is challenging to get y by itself sometimes, okay? And that is the reality. So if it is challenging to get y by itself, we are going to use implicit differentiation, okay? And sort of as a preview to that, before we go on break, this question. Anybody want to solve that for y? I have x cubed y to the 5th plus 3x equals 8y cubed plus 1, right? I think real quickly we might look at that and say, you're crazy. I don't want to solve for y there, right? That looks so complicated, but we're going to be able to find the derivative of that, okay? Or like, what about this question? Anybody want to try and get y by itself there? I hope not. Right? Oh no. Yeah, exactly. This one's not so bad. I could get y by itself. But then I'd have to use chain rule, quotient rule, exponentials, power rule. Ooh. Or, ooh, this is a juicy one. It's going to be real hard for us to try and get y by itself, right? So when you see these questions on a quiz or on an exam, anytime the x's and y's are mixed together, I want you to think, oh, I better go to section 3.8 and think about those examples, okay? So that seems like a good place to pause, right? So let's just go back up to where we're gonna pick up when we come back from break, which is here. And let's see, what time is it? It is 9:57, so let's be back, or sorry, 8:57. No, 7:57. Let's be back at 8:15 a.m. Okay, so we'll take a little bit of a longer break. We've got a few examples to work through when we come back, but I think we set a really good foundation here. It's more just think about all the rules that we learned so far. We're gonna need them to help us with these new types of problems, okay? So I'll see you folks back here in a little bit. All right, so before the break, we were talking about this idea that sometimes we know that we can solve for y and all is fine and well, but sometimes we cannot. And that's why we need this alternative technique. There were some really great questions asked about the derivative. Ooh. Hold on. So many technology issues, my goodness. Okay, let's try this again. That when we have the derivative of x, what do we get when we take the derivative of x? we get 1. And what if we take the derivative d dx of y? We end up with y prime. Good. Okay. And so this is going to be really valuable for us as we go through. We're going to be using all the rules that we already know. And we're going to just make sure that anytime we're looking for a derivative with respect to x of x, that's going to be 1. But if we're finding a derivative with respect to x of y, that's going to be y prime. Okay. So, I always ask you, tell me what rules you think you're going to need. And in a moment like this, I think it makes a very long, complicated looking problem a little bit simpler. Okay. So let's start with this x cubed y to the 5th. What rule or rules do you think we're going to need to use here? I see product rule, excellent. Power rule, excellent. Product and power. All right. And I'll leave it up to you, but I know at some point, if I have y to the 5th, that I probably need a y prime to appear. And so either you write it like implicit, like you see the y mixed in with the x, or some students just write y prime as a reminder that they're going to need that y prime. Okay, so I'll kind of leave that up to you. But either way, when you're finding that derivative and it has a y in it, we want to think at some point we're going to use a y prime. Okay, so what does this setup look like? U is going to equal x cubed. V is going to equal y to the 5th. Okay. What is our du equal to in this case? 3x squared, good, 3x squared. What about our dv? All right, I see one brave soul has an answer here. Do we agree? Do we disagree? All right, so we're gonna need the power rule here. So 5y to the 4th, but because y is a function that we just didn't wanna solve for because it was so gross looking, times y prime, and that's where our chain rule comes in, okay? All right, let's write out the setup for a few more of the other parts. Let's go with this one, the 3x. What rule or rules will we need to find the derivative of 3x? Good. We're going to need that constant multiple rule. Okay. And let's do the right-hand side. Let's take a look at this 8y cubed. What rule or rules will we need for the 8y cubed? Constant multiple, good. So we could say constant multiple. You could say power, and implicit or chain could actually be another way to write that. So implicit, chain, or y prime. I think all 3 of those tell us we're going to need a y prime at some point there, right? And last but not least, let's sneak in this little 1 over here. What do I need to take a derivative of 1? Yeah, 1 is just a constant. So we have a blue, a purple, a pink, and a green part, all right? We're going to string it all together first. And we're going to make sure that we do every single piece and make sure that equal sign is still there, okay? And so when we set things up, we will end up with x cubed times 5y to the 4th times y prime plus 3x squared y to the 5th. That's all the things in blue. Plus derivative of 3x is 3. That's the thing in the purple. Equals, let's see, 24y squared times y prime. That's the thing in the pink. Plus 0, because the derivative of 1 is 0. Okay. So let me just pause here for a moment. How we feeling with all the derivatives laid out there? All right. So earlier we had a really great question like, can we leave it like that? Now this is the calculus part, okay? In order to finish the question, I want our answer to be y prime equals, okay? So we're gonna have to get y prime by itself. So to complete the problem, we must get y prime by itself, okay? So if you leave it here, you are not finished, all right? You need to get y prime by itself. The nice thing about this is we're going to think about y prime as like terms, and we're going to try and collect all the things that have y prime on one side and everything else on the other side, okay? So if I think about this, I notice that this first blue term has a y prime, but so does this pink term. So what I'm going to do is I'm going to take this 24y squared y prime and I'm going to subtract it to the other side. Okay. In the same step, I'm going to take these two that do not have a y prime and I'm going to move them to the other side. Okay, so we're getting everything that has a y prime on one side, everything that does not on the other side. So we end up with 5x cubed y to the 4th y prime minus 24y squared y prime equals negative 3x squared y to the 5th minus 3. Right? Now, what's the benefit of collecting all of the y primes on one side? Exactly. The reason why we're collecting all the y primes on one side is because now we can say y prime is common to both terms. So if I factor that out, that gives me this. And the benefit to this, how do I get y prime by itself, right? That's my end goal. My end goal is to get y prime by itself. That is perfect. That is maybe the most beautiful way to say that. Divide by that whole chunk in the parentheses, right? This whole thing, since it's times y prime, let's just divide it. Done. Okay. It's okay if your head is kind of swimming a little bit right now. This is a lot of work, right, on one screen. But if we think about it step by step, we began by identifying all the rules. Since we had all those rules, we were able to show our setup where we need it, right? And find the derivative of each part using the rules that we identified. And then the calculus part was done. To complete the problem, we just had to get y prime by itself, and that was a lot of algebra. So we clustered all the things with y prime on one side so we could factor it out. And then we were able to divide by that chunk inside the parentheses to get y prime by itself. Okay. All right. Shall we try another one? Are we feeling up to the task? I hope so, because we have like 5 more examples. Okay. All right, so number 6, let's get started the same way. Let's identify our rules. We can write it in whatever way sort of feels more natural. Again, we could say chain or implicit or y prime. All of those are kind of valid. But let's start this time with this, the x cubed tangent y. What rule or rules do we need to find that derivative? Good, good. All right. I'm going to list product rule here first because that's going to be my initial setup. Okay. I forget who it was. I think it might have been Vince. You said it so well last week. You were like, so it's situational, like the order in which we do things. And that is exactly right. Our first step in the setup here should be product. Then to do the x cubed, we'll need power. To do the tangent y, we'll need trig. And we could call that chain or implicit or y prime. Okay, so however you want to call it. I think a lot of us are saying implicit, so let me stick with that. All right. Now, if I were to think about what I need for the purple, situationally, I would start with the product, right? Because I have y to the 10th times secant x. Now, I'm going to need power and implicit for the y to the 10th part, but I'm going to need trig for the secant x part, okay? And then this one I feel like you folks know super well. This 2x is just going to be a constant multiple, okay? So we've got a lot of setup to do, but that's okay. We're going to take it step by step. We're going to keep our work super organized and then see what we end up with, okay? So let's start over here with the blue. U equals x cubed, v equals tangent y. I'll pick the more straightforward one. I'll tell you du is 3x squared. You folks tell me what dv is for the blue one. Ooh, super close. I bet we could modify what you have there. Ah, yes. Okay, so I'm going to write secant squared y, all right? So secant squared y and times y prime, okay? This right here, forgetting this, if you don't have any y primes in the whole thing, you're not going to have anything to collect on one side. Like you won't have an answer, okay? So having that y prime where appropriate is so important, all right? Additionally, we want to make sure that we have our y prime everywhere we need it, because if we're missing it somewhere, as we cluster all the terms with y prime and we forget one, we won't be collecting all the terms we need, okay? All right, so let's try our setup for the purple one now. U equals y to the 10th and v equals secant x. Take a moment, tell me what my du and my dv are. All right, can anyone confirm whether they agree or disagree with Luca's contribution? We've got a 10y to the 9th times y prime. Okay, we've got a couple agrees, good, me as well. 10y to the 9th y prime, good. And our derivative for secant x, good. I think now might be a good time for me to tell a funny story. So I used to teach high school, and it was, I think I was teaching maybe Calc AB or something. Anyway, we had this whole exam about derivatives, and we were getting to the derivatives of trig. And apparently I had decided that I wanted to have secant as like so many functions on this exam. But I was kind of rushing, and I had to make all the copies, right? Because it was like paper copies for everyone. So I had to make all the copies for everyone, and I didn't have time to make an answer key before I printed them out, right? I normally like to check my work so that I'm not printing things with a bunch of mistakes. And so I give out the test, I start to make my answer key. And so everyone is sitting there working on the test. And as I'm working on the answer key, I realize that autocorrect has changed every function into this. And so and I had used it like 10 times on this test, right? So there's just like this all over the test in front of a high school class. And I had to stand up there and be like, okay, folks, I'm gonna need you to change all of this back into this. Yeah, it was one of the most embarrassing moments in my teaching career, you know, but you got to go with it. I was like, please don't tell your parents because you're all like under 18, right? But thank goodness now I try my best. I learned my lesson the hard way. Make sure you make answer keys in advance so that you don't make that mistake. All right, so let's not forget our very simple but important part of this equation. I'm going to find the derivative of 2x. So the derivative of 2x is going to just be 2, okay? All right, so we've got a lot of setup here, right? We have the thing in the blue, we have the thing in the purple, we have the thing in the pink. We need to make sure we write out every single thing. And before you start, I might even encourage you to make sure you have that y prime everywhere you need your y prime, okay? So let's write this all out. We've got x cubed secant squared y times y prime plus 3x squared tangent y. All of this is the blue, plus the derivative of the purple part, So let's see, we're gonna get y to the 10th secant x tangent x plus 10y to the 9th y prime times secant x, and all of this is in the purple, equals what's in the pink? That derivative is 2. Okay, so we've set up everything, we've got all of our derivatives, we are done with the calculus part. All right, in order to finish the question, we need to collect all the y primes on one side so that our final answer is y prime equals something. Okay, this term, this term has a y prime, this term has a y prime, so I'm going to kick all the, oh, that's not working right now. Oh, there we go. Okay, so the two terms in the yellow, those have the y prime. I'm going to make everything else go to the other side. And I'm going to get x cubed secant squared y times y prime plus 10y to the 9th y prime secant x equals 2 minus 3x squared tangent y minus y to the 10th secant x tangent x. All right, so I'm only keeping the ones that have the y prime. And the reason is so that I can factor it out, right? Because once I factored it out, I can just divide by the thing in the parentheses, done. So y prime, parentheses, all the stuff that's left over. And then our very last step, we're gonna divide. I never leave myself enough room, but let's try squeezing this a little bit. Whoop. All right, so y prime equals the right-hand side divided by the chunk inside the parentheses. All right. So let me pause here for a moment. Let's see if we have any questions. Oof, that's a great question. I think when I do these kinds of problems, it's not really a check, but I will often make sure I'll go over this part twice. And the reason why is because that setup piece, right? If this is incorrect, it doesn't really matter what I do with the rest of it. I'm going to be missing something. And so in some ways, the very first part we did, double checking that part even, I think will help minimize those mistakes. Like make sure, did you use a product rule? Did you use your y primes? Did you use a quotient rule if you needed to? Okay. Now, I know that if you look at a lot of online resources or you're watching videos, they don't necessarily write this part out. And so as you're watching someone else do it, or you're looking at a website that shows you the steps, this part is something that they talk about, but they don't actually write down. And one thing I noticed is on this last quiz, a lot of folks were jumping right to here. Okay. I think that's really hard to do in the beginning. And so sometimes just by practicing, oh, okay, I got my product rule, or oh, I need a quotient rule, writing that down. I know it's more writing, but it helps me make those decisions better, and it forces me to practice making the decisions instead of watching someone else do it and be like, oh yeah, that makes sense, that makes sense. Like, it forces me to engage more in the process. So it's not a check necessarily, but I think the more you can make sure you know what decisions are being made, then the rest of it should flow. Okay. Sophia has a really good recommendation. I think also it's a small thing, but sometimes when I'm checking my own work, I don't see the mistakes. And so if I went from like blue to purple to pink, as I did it the first time, when I come back and check my work, I might do it in a different order, like purple and then blue and then pink. Because sometimes just like scrambling that a little bit in my brain forces me to look at it differently. So it's a small thing, but I think sometimes when I do things in a different order the second time, it helps me find more mistakes. Okay. All right, let's go ahead. Highlighters. I know there's so many fun colors with the tablet for sure, but highlighters I think are definitely incredibly helpful. All right, we got a little bit of lag going on the screen, but let's take a look at example number 7 here. All right, so find the derivative of e to the x over x squared equals y cubed. All right, now we have a couple choices here. The way that it's set up, what rule are they asking us to use on the left-hand side? Yeah, they're asking us to use quotient rule, right? Now, I don't know why I have this, I don't know if it's like a personal thing with quotient rule, but it just like often brings more fractions into things. And I don't personally like that. And so I think sometimes I sort of like impose that on my students when I'm talking about it, right? But Sophia's correct. We could do a little bit of algebra right up front and actually use the product rule instead of the quotient rule. So let me throw that out to the whole class. Would we prefer to use the quotient rule right now for practice, or do we want to think about how we could use that product rule? All right, I see some quotient, some product. Either is good practice. Okay, let's go with product then. So if I were doing this problem, I would do product. I would sort of do a little bit of pre-work. I would multiply that x squared to both sides, and I'd get something like this, right? And in the middle of an exam, that might just make me feel more comfortable because I don't see any fractions, right? We are going to take the derivative of both sides. So let's do our color coding. We're going to figure out what rule we need for the right-hand side, and then what rule we need for the left-hand side. And so I think for the the left-hand side, we just need our exponential, exactly, right? And on the right-hand side, we're going to lead with product rule. And then we're going to use power for the x squared. And then for the y cubed, we're going to need power and implicit, right? We want to remind ourselves we have that y cubed, there better be a y prime somewhere there. All right, let's set this up. U equals x squared. V equals y cubed. Du, I think we all know by now, is going to be 2x. And dv, if you wrote 3y squared, I would be so sad for you. You would be so sad for you. You got your 3y squared. Don't forget that y prime. All right, so that's sort of like a good time to pause and make sure that you've got everything there. All right. I'll also go back and write down what Matt put in for the derivative of e to the x is going to equal e to the x. All right, let's put everything in to the appropriate rules. We're going to have e to the x equals, let's see, 3x squared y prime plus 2xy cubed. All right. Now, before we finish the problem, let's just make sure we're okay with this part, right? Let's do a double check. Did we miss any y primes? Did we use any rule in the wrong way? All right. Anybody find any mistakes? Or are we okay? Yeah, I think we're good as well. Okay, so now we might want to say, where is the y prime? How many of them are there? There's only one. So that means that we just need to subtract that 2xy cubed and then divide by whatever's in front of our y prime. Okay, so 3x squared y prime equals e to the x minus 2xy cubed. And then we divide, we get y prime equals, and that's how we know we've gotten to our final answer. Okay, so let's get this back on one screen. Take a look at that. I know it had an e to the x in it, but this one actually ended up being not as bad as some of the other ones that we saw earlier. All right. Yes, it was pretty tame. All right. Well, don't worry, we still have 2 more examples to go. I think it'll be sort of less tame and then a little bit more tame, okay? So let's go ahead and take a look at example 8. All right, so we have the derivative of sine xy plus 12y x cubed minus 100 equals the natural log of y, okay? So let's parse this out. Let's talk about rules. We have this chunk with the sine xy. We have our 12, let's put this one up here, 12x cubed. We've got our minus 100, and then we've got our natural log of y, okay? So what rule or rules do we need for any one of these? Let's do a little bit of that brain dump. Good, we're gonna need trig and chain. I would say there's one more rule we need for this blue one. Yeah, we're gonna need a product rule. Why are we gonna need a product rule? Yeah, because it's x times y, okay? That one, I'll tell you, is a little sneaky. So we gotta be really looking out for that, okay? What about for, let's see, what else have we seen in the chat? Constant multiple, yeah, I would say maybe this purple one would be a constant multiple, and maybe that power, right? I saw the natural log one. So we want to use the natural log, and then we might want to make a note to ourselves, implicit or y prime. And then, you know what? We did all the hard part. Let's not forget about the easy part. That minus 100, gotta remember that's constant. So if you have a minus 100 in your answer, you forgot about the easiest part, okay? Which can happen because we're doing so much complicated stuff. But that's why I think when we label and just force ourselves to think before we get started, it helps us minimize those mistakes, okay? So let's set up our product part for this blue one. U equals X, V equals Y. Du should equal 1, while dv, because y is a function, is going to be y prime. Okay. All right. So sine of xy. I got to take the derivative of the outside first. Then I have to multiply by the derivative of the inside. Plus 12x cubed, if I take that derivative, 36x squared, minus 0, because that was the pink part. Now, what am I going to have on the right-hand side? That derivative of the natural log of y.
Is it 1 over y prime?
It is indeed 1 over y. That's my derivative of the natural log, but because it's a y, times y prime. Okay? And that corresponds to the green part. All right? So if I were working through this problem, I would make sure that I pause and that I double check this step, right, before I move further, because the calculus is done. And so if I've done that wrong, then the algebra is going to be wrong. All right, great question in the chat. Why do we have xy prime plus y? All right, this part right here. So if we think about this, we said that we needed chain rule, right? We have an outside function, sine, and the inside function is xy. And so if we think about our derivative, we better have f prime of g of x, right? That's my outer function, times the derivative of the inner function, g prime of x. And so the cosine part is the derivative of the outside, whereas the xy prime plus y is the derivative of the inside part, because xy is the inside of sine x. Does that make sense? I'm really glad you asked that question. I think a lot of people probably have that question. Okay. All right. So once our calculus is done, now we just got to get it as a y prime. So we're going to collect all of our terms that have a y prime in them. But before we do that, I think we might need to simplify this part first. In fact, I think it would be useful if we distributed the cosine xy to the first term and to the second term. Okay. So we're going to get xy prime cosine of xy plus y cosine of xy. And that's just the blue part distributed. Okay. A lot of times when we have that chain rule where we have something inside a cosine or a sine, we need to distribute in order to move forward. Okay. I'm going to stack this right-hand side to be y prime over y. And now I think we can identify here's a y prime and here's a y prime. So we want to cluster those together on one side and we want to have everything else on the other side. Okay. What term would you like to move? Because I think we have some choice here. Do we want to move the y prime over y? Do we want to move the xy prime cosine xy? Yeah, I think that might work out better too because we have less things to move. I'm going to move this one to the right-hand side. Okay. So I will get y cosine xy plus 36x squared equals, I'm going to go ahead and factor out the y prime in the same step. Okay, so I'm going to have y prime 1 over y minus x cosine of xy. All right, so I moved all the y primes to the same side and I factored in the same step. Now, all I have to do is divide by the chunk in the parentheses, and I'll get y cosine of xy plus 36x squared over 1 over y minus x cosine of xy. All right. So a little less tame than the last one, but I think showcases some of like a different strategy that we haven't really seen before, which is this idea of the distribution. Okay. So I'll give us a moment to see if we have any questions, and then we have one last example for the day. All right. I don't know if there's no questions or too many questions, but either way, let's take a look at example 9 here. All right, that you can always ask questions later on. Okay, so this last question is find the equation of the line tangent to the curve x squared plus y squared equals 25 at the point 3, -4. Okay. Now, one of the things I noticed on the quiz was that some of us didn't know how to write our final answer. Like we found some information, we're like, ooh, I'm going to take a derivative, but then we didn't do much else with that. Okay. And so as a reminder, let's think about when we see that tangent line and we want to find the equation of a tangent line, we want to think y minus y1 equals m x minus x1. Like that is our goal. At the end of the day, we need to fill in an x1, a y1, and an m. Okay, and so if your answer doesn't look like this with numbers for the x1, y1, and m, then you didn't get to your answer. Okay, so we want to be really careful about that, making sure we communicate to people, right? So me, I'm looking at your work, you communicate to me that you understand what the question is asking. All right. All right, well, let's start with what can we fill in? I think we can fill in some information here. Yeah, we have the x1 and the y1. Very good, very good. Okay, so I'm going to go ahead and put the 3 in for the x1 and the -4 in for the y1. Okay, so we're going to put the 3 in for the negative, or 3 in for the x1 and a -4 in for the y1. And Abby, you are correct. We need a y prime. So let's take our function. Okay, we could solve for y, but because we just learned about this new skill, let's try this new skill. Okay, so what do we get for our derivative of x squared? Good, 2x plus, what's the derivative of y squared? Yeah, 2y prime equals, don't forget to take the derivative of the other side. What does the other side go to? Yes. All right. Now, I know I didn't write out the rules this time, but if you realize that maybe I tend to make those mistakes, it might be good to just write them out just like we did up here in the different colors or all in the same color, whatever makes your life easier, but just like thinking through the process before you start writing, okay? Now, we want to get y prime by itself. So what should I move? I agree. So 2y prime equals -2x. Good. Y prime equals -2x over 2y. Should I simplify? Should I not? Yeah, I think this is a pretty good case for, it will take like 1 second to simplify. All right, we get y prime equals -x over y. But how do I find the m for this particular equation? Because it's not going to be -x over y. Good, good, good. Okay. Now, the reason why I'm sort of pausing and asking us to answer that question here is because I've seen some students who get to this part, you get to your derivative, but I'm asking you for a specific number and you just stop right here, right? So some of us did that on quiz 6. Like we found the derivative, but then we didn't plug those numbers back in. Okay, and so if there are numbers, we want to be really patient. We don't plug them in until the very end. But once we get to that end, we do plug them in. So 3 over -4. That means our slope is 3/4. All right. Now, yes, we did a lot of math, but we didn't write our final answer yet. So if you stop here, all you showed me is you know how to take a derivative. Okay. You did not show me that you understand what the equation of a line tangent is. So we got to go back in. We have to fill in our x1, y1, and our m. So we're going to get y minus -4 equals 3/4. x minus 3. All right, this is absolutely fine. This is also fine. Please do not simplify beyond this. This is fine, okay? So we learned a new technique. We went through some pretty complicated equations, and then we sort of finished off with, we can always ask about tangent lines. The techniques that we use to find the derivative, to find the slope, might be different. But at the end of the day, anytime someone says tangent line, we want to think this equation. Okay. So that is where we are going to finish today. Are there any questions about 3.8 before I make a few quick announcements?